energy, which is 1/2 omega transpose I omega. I'll give you some time to write. I'll give it back again. I'll give you some time to write. But just bear with me for a minute, please. This is 1/2. Omega is a vector, it's a column here. The transpose is just a row. Here it is, omega sine theta, negative theta dot, omega cosine theta. Like I said, this is just a bracket for a row. Okay? And I have the inertia matrix here, 80, 81, 1, zeros, and I have ml squared over 12 outside, times omega again, but now it's not a row, it's just the column, omega sine, negative theta dot omega cosine. So multiply it at any order you like, but do it, of course, once at a time. You cannot do it faster than this. Once at a time. Either this guy times that guy, or either this guy times that guy. So let's do it here. It's t is equal to ml squared over 24, f and 12. I'll multiply this guy times that, the matrix. So I will get a row. Actually, it's very easy because it's diagonal. So 80 times the first, 81 times the second, and 1 times the last. This is very easy. And this is times your omega sine, negative theta dot, omega cosine. The rest simply multiplying a row times a column. So this is ml squared 24. Again, first times the first, this is 80 omega sine squared theta. The second together is 81 theta dot squared. The last together is omega squared cosine squared theta. There was omega here. So this is your kinetic energy. The whole kinetic energy. Just add the potential to it and turn the crank. Okay? So you got some training on that. Now you can speak with a good conscience. You can solve whatever you like. Any question? Any question about that? Because we're going to really depart a very large departure. They're going to completely change gears. Yes, go ahead.
Where is the center of mass of the composite body?
I did not, it's somewhere here, but I did not need to compute it because the kinetic energy, here is the formula that will apply. It's either this formula, right? And in this formula, you need the velocity of the center of mass, the moment inertia about the center of mass. That's correct. So I need to know the center of mass. But if I'm doing only rotation about a fixed point, which is the case here, you can exploit and reduce down this relation and exploit it to use this relation instead. It's simply rotation kinetic energy about the fixed point. There's no translation kinetic energy again.
Oh, so that already includes the first term?
Oh, yeah, exactly. You can compute it either way. So in this particular problem, you can go, if I'm doing it blindly, I will do it with the center of mass, and here's the center of mass, and
I see.
okay? And of course, you'll get the exact same answer.
But I still need to find the location for the potential energy term, right?
That's very good observation. That's right. Because the potential energy would be what? mg times the h. H of what? It's h of the center of mass. So you need to find would be 4 over 3.
For the potential, can you calculate both separately? So going to the center of mass of the 12 and the center of mass of M.
Yeah.
Do it separately?
Yeah, that's fine.
So you don't need to find the center of mass of the whole thing and
That's okay. Yeah, we can do that. Do you have any question, please? Should you, do you need this? Anybody need? Because nobody needs this? So I just have it like this in order to be able to copy. Okay, I'll erase a lot of stuff because we're, like I said, we finished dynamics. There's no more dynamics, by the way. You can, and the information that you have so far is sufficient to solve all problems in the world that we live in the scale that we feel. Don't go to the planets rotations. If you don't go there, then you're fine with what you have now. We're gonna talk about more deep stuff, just to convince you not to do a PhD, or if you love science, to convince you more to do a PhD. So almost between 1/3 and half the course, they will be in the final, in addition to Lagrange mechanics. Newtonian mechanics will not be in the final. There is now on. Okay. Now on, I'm talking about something that is optimization. As you suggested, Shahuz, as you can see from the title, it has literally nothing to do whatsoever with all what we have been studying. Indeed, if you did not get anything from the course, you can start very fresh now. Okay, at least you will get 2 problems in the final out of 4. Okay, and 2 homeworks, not 2 homeworks, 1 homework and 1 quiz. Because today's homework is on Lagrange mechanics. That's done, that's fast. It's literally optimization, it's 206. It's a nice summary of 206. Okay? Or if you're doing your prelim next week in dynamics and control, it will be a good review for you. Okay, optimization. In optimization, as the name may tell, we were interested in just minimizing the function or maximizing the function. Let's just use some convention now. So let's say we're going to minimize functions. So I want to minimize, I have f of x and I want to find x that minimizes f. This is pretty simple, right? We write it in a standard form as follows. Minimize f of x over x. So my x is the free variable, is my design variable, okay, that I'm looking for. I'm looking for its optimum, okay? How do you solve this problem?
Is it linear or not?
I don't care. How do you solve this problem?
Find stationary.
What?
Find stationary.
Yeah, so don't use glossy words, please. Use high school terminology, okay? Yes, differentiate. You got differentiation in high school, right? I guess. So just df by dx equal to 0, get your x star, the optimum value. I'm done, right? Okay, what about if you have 2 variables? Like I'm minimizing a function of 2 variables. It's not only 1 variable, it's x and y. And my free variables now are x and y. How can I solve this? Yeah, so I was differentiating with respect to 1 variable, now I'm going to differentiate with respect to each variable. It's partial f, partial x equals 0, and partial f, partial y equals 0. These are 2 equations in 2 unknowns, the x and y. Get your x star and y star, correct? Very good. So if you want to just use a little bit more formal words, this is equivalent to what? The vanishing of the gradient, right? Because what's the gradient? It's partial f, partial x, the first component, partial f, partial y, the second component of that vector. So it's as if both vanish, it's as if the whole vector vanishes. So the gradient should be 0 at the optimum point, okay? Any question about that? Please, if you have any question, remember, as you can see, it's really totally new topic. It has nothing to do with your, whether you studied or not for this course. Whether you got 0 in the midterm, I don't think that anybody will get 0 unless you didn't show up or you just in the line. Okay, but now I'm interested in minimizing a function of 2 variables. Here is my free variables, but you know what? They are not quite free. we literally write it like this, informal terminology. Subject to this constraint, some function of x and y is 0. Okay? And by the way, this is, you know this problem? Function of two variables subject to one constraint. This is what you're going to see in the prelim in dynamics and control optimization. It doesn't get harder than this. The problem will be exactly like this. And then they will maybe ask you something extra on state the KKT conditions. But the problem itself, to get the numbers and play with things, will be exactly on this one. And you know what? I can solve this problem without knowing anything about 206, just the high school thing. How you do?
Plug in the constraint too.
3 equations, 3 unknowns.
That's a great plug in. Use the constraint. Hopefully, I'll write it. Mathematicians will relate without loss of generality. Without loss of generality, your constraint calculated on this form. Y minus h of x is 0. You can try to play with your constraint to get one variable in terms of the other, right? Y as a function of x. Y equals h of x. So y minus h of x equals 0. This is your constraint. Okay? Then what to do?
Put
Well,
y game back.
I'm going to plug it here. To get rid of all the y, I'm going to have a new function. So my f of x and y, I'm going to remove every y and put it just h of x. Right? This is simply a single function of scalar function of a single variable. Right? Scalar function of scalar variable. How to get the optimum of this? This is function of x only. How to get the optimum? That's the very first problem that we learned in high school, right? So just substitute your constraint. You got this guy. Okay, how do you solve it? How do you get the optimum here? How do you get the optimum here?
Solve for x.
Differentiate.
Differentiate, and its total derivative now is function only of x, right? Do it and solve your problem, but we'll do it here abstractly because I want to get something. Let's do it abstractly together. Differentiate this function with respect to x, please. It's function of two arguments. Partial little f, partial the first argument, plus partial little f, partial the second argument, times the derivative of the second argument with respect to x, which is h prime. Okay? Any question about this?
That y is just h of x.
This is no. I'm given a function of x and y from the beginning.
Oh,
Say
okay,
x squared plus y squared. Gotta differentiate with respect to y. Okay? And multiply by this guy. Then the remainder, maybe function of x and y, I'll remove any y with h of x. That's from the beginning. This is df by dx. I'm going to equate it to 0, right? This is the optimum. Correct? So at the optimum point, I have, I'm going to write fx for partial f, partial x, just to save some time and energy. This is negative fy times h prime. This is at the optimum point, I'm going to denote it by star. Okay? Any question about that? I'm doing it abstractly. If I have a problem, it would be much easier to solve, right? I just have here a function of x and solve it and finish. But I'm doing it abstractly to show you some. Any question about this blue equation? So the gradient of your function is not necessarily 0 at the optimum, because it's a constraint. If it's an unconstrained problem, yeah, certainly your gradient has to be 0. But in a constrained problem, your gradient of the function may not be 0, because at this point, it might not satisfy the constraint. You have to take into account your constraint. So what is your gradient in general? Well, it's partial f, partial x in the y direction, plus partial f, partial y in the j direction. At the optimum point, I'm going to substitute from here. fx is fy times something, so I'm going to get fy as a common factor. Negative h prime in the I plus 1 in the j. Right? This is at the optimum. Now what about the gradient of your constraint? What's that? What is the gradient of your constraint? What's the gradient of the constraint? Come on. Come on guys, what's the gradient of the constraint? Here it is, you have a function psi of x and y. Here is your psi of x and y. What is the gradient?
Minus derivative.
Yeah, differentiate with respect to x, you get negative h prime in the I. Differentiate with respect to y is just 1. Right? What about this? What do you get from these two equalities? I get the following very important rule, is that the gradient of my function at the optimal point is equal to some constant, right? This is a number, because it's evaluated at the optimal point. Some constant times the gradient of the constraint at the optimal point. Correct? The gradient of this guy is some number times the bracket, and this is exactly the bracket. Correct? You're multiplying the whole vector, every single component of the vector, by just a scalar, a constant. I call it C. When you have a vector that is equal to a constant times another vector, what does it mean?
Eigenvalue.
No eigenvalue.
Scalar.
Eigenvalue has to do with the matrix, right?
Direction same.
This is a vector, just a vector. It's a constant multiple of another vector. What does it mean?
Dependent.
Depend, I know, you're thinking of 208. Yes, they are dependent. Geometry, what does it mean?
Same direction.
Same, they are parallel, right? They are parallel together. So this is exactly the Lagrange multiplier rule in optimization. Lagrange multiplier rule. What's that? Is that the gradient of your objective function is not 0 at the optimal anymore because it's a constraint, but it's parallel to the gradient of the constraint at the optimum point. Okay? Give you some time to write until I read this.